Hey class, we're going to start Calorimetry part 1 of a several day lesson over this term. Depending on where you are at, you can hear it be called calorimetry like I do or calorimetry. Either way, we're talking about the same thing. So let's introduce what is calorimetry. This is the process of measuring the amount of heat that's either absorbed or released in a chemical reaction. One thing, in order to do this process, we use a device called a calorimeter. And this is the device that actually measures the amount of heat in the chemical reaction that is being absorbed or released. Before we get into calorimetry, we have to understand a new important concept called heat capacity or specific heat capacity. The more heat an object gains, the hotter it gets. And so all substances are going to change temperature when they are heated. However, the magnitude, or basically the number of the temperature change produced by a given quantity of heat, is going to vary from substance to substance. So, for example, if I give something 500 joules of energy, one substance might only increase to 23 degrees Celsius, but the other one might increase to 70 degrees Celsius. And you probably see this with metals versus water. Metals tend to heat up very easily and quickly, whereas water takes a lot more heat, a lot more time to get to a certain temperature. So the temperature change experienced by an object when it absorbs a certain amount of heat is something called heat capacity, which is denoted by the letter C. So we're going to talk about heat capacity, and you can write down this stuff if you want, but this is not the equation that you're going to see on your homework. I'm just introducing this to you because we will build off of it. So heat capacity is defined as the amount of heat required to raise an object's temperature by 1 Kelvin or 1 degree Celsius. And one thing you should know about heat capacity is it does not involve mass. Higher the heat capacity, the more heat it's going to take to raise the temperature. And our formula is C equals Q divided by change in T. So let's talk about each part of this equation. C stands for heat capacity. Heat capacity is units in joules per Celsius or joules per Kelvin. Then Q is the amount of heat that has been absorbed. The units here are joules since we are talking about energy. And then our change in T is going to be our final minus initial in order to figure out that change. And your units can be in Celsius or Kelvin, which is a lot different than what we've been working in the past. In the past, everything had to be in Kelvin. So here, people are shocked when we're allowed to use Celsius. And the whole reason for this is because of this delta sign, this change. Since we are finding the change in T, we are allowed to use either units, and that is because the difference between freezing and boiling for both of these units is actually 100. Celsius, things freeze at 0 and boil at 100. For Kelvin, they freeze at 273 and boil at 373. Both of these differences are a difference of 100. So they're on the same scale that way. Now, one thing to know about heat capacity is it's an extensive property, which means it depends on the amount and size of a substance. And for scientific purposes, it's actually a lot more convenient to report heat capacity as an intensive property because we don't want to have to depend on the size or the amount of a substance. Oftentimes in science, we tend to stay away from heat capacity and tend to focus on something called specific heat capacity. And this is what your homework is going to actually be about today. So I'm going to go ahead and star this. This is the important slide. Specific heat capacity is actually denoted with the letter C with a little s down below to denote specific. It's defined as the heat required to raise the temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius. The major difference between heat capacity and specific heat capacity is we are now actually taking into account the mass, so that way the specific heat capacity is not going to be reliant on it when we give that value. Just like heat capacity, the higher the specific heat capacity means the more heat is going to be needed to raise 1 gram of a substance up in temperature. One thing that I do want you to know, and I do have it bolded and underlined, and it says no, is the specific heat of water is 4.184 joules per gram for every degree Celsius. And this number might actually sound familiar because 4.184 was how to convert between joules and calories. So the unit for specific heat is going to be dependent on units for the calculations. So our formula for specific heat is actually rearranged a little bit. Here I have Q, which stands for heat. Again, the units are joules, times specific heat. And the units here are joules divided by grams times Celsius, or joules divided by grams times Kelvin. And then we have change in T here, final minus initial. This can be in Celsius or Kelvin. And the last one is mass. Now mass, because of our unit up here has grams, our mass must be in grams, not kilograms. So here we need to understand the equation. When you have a positive Q, that means that the sample or system that you're observing is absorbing heat, and so its temperature is going to increase. Whenever you absorb heat, we need to remember that absorbing heat means you are endothermic. Whenever you have a negative Q value, this means that the sample, what you're looking at, whether it be the systems or the surroundings, is actually releasing heat. So you're giving it up, and typically your temperature is going to decrease when you release heat. So these are going to be exothermic reactions. We're going to look at 4 examples, finding each one of these 4 things. So for example, number 1, we're going to find the specific heat capacity. So it says an energy of 645 joules is applied to a sample of glass with a mass of 28.4 grams. Its temperature increases from negative 11.6 to 15.5 degrees Celsius, and we need to calculate the specific heat of the glass. One thing, let's go through our equation. Remember, Q equals mass times our specific heat times our change in temp. And the one thing that we need to look at is pay attention to the wording. Here it says 645 joules is applied to the sample. So this amount of work is given to the sample. It's going to be a positive value. Joules goes in for Q. So we know that Q is 645 joules. Mass. If we look at this, our mass is given, and it's given in the correct units, which is 28.4. If this was not given in the correct units, you have to make sure to change it. The next one is specific heat, which we do not know. I'm going to put it as X. And the last one is your change in temperature. So remember, your change in temperature is final minus initial. So here my final was 15.5 minus my initial, which was negative 11.6. So my difference is going to equal 27.1. Now it does not matter that it's in Celsius, that's okay. Then we can plug in things into our equation. 645 equals 28.4 times X times 27.1. We can go ahead and solve using our algebra skills. And then here we can divide, and you get X equals 8.33805415552. Now we want to make sure that we go to the proper number of sig figs. Here, this one has 3, 3, 3, and 3. So we're going to go to 3 sig figs here. So 0.838. And we have to make sure we're using proper units. So here our proper units is joules, because that was what our energy was, divided by, we divided by our grams. And then here, since we use Celsius, our unit is degree Celsius instead of degree Kelvin. Example number 2, we're going to be finding heat. So remember, heat is going to be our Q value that we're trying to find. So Q equals M times CS times change in T. We don't know our Q, so I'm going to go ahead and put X in for it. And we got to read our problem for the rest of it. It says the specific heat of iron is 0.450 joules per gram degree Celsius. So here I'm going to plug that in for my specific heat, 0.450. Notice here it says joules per gram degrees Celsius. Yep. Then it says how much heat in kilojoules. So here I want to know the heat in kilojoules. That's important. Is required to raise the temperature of a 5-gram sample. So here's my mass, 5 grams of iron from 22 to 53. So here to find my change in T, 53 minus 22 gives me a difference of 31. So this is going to be 31 degrees Celsius. Then we can plug in what we know. We don't know my Q times my mass times my change in temperature times my specific heat. And when you guys go to solve this, you're going to see that Q actually equals 69.75. One thing to note though is that here my specific heat is in joules. So when I solve this, this is actually in joules. However, if you read the problem, it wants it in kilojoules. And we've already learned how to convert between joules and kilojoules. In order to do that, there are 1,000 joules in 1 kilojoule. So when you divide it by 1,000, your answer, if we were doing it, 0.0698. 3 sig figs, that makes sense, 3 sig figs in the problem, and my answer is in kilojoules. Finding example number 3, finding the change in temperature. It says 1,674 joules of heat are absorbed by 25 milliliters of an aqueous solution of NaOH with a density of 1.10 grams per milliliter and the specific heat capacity of 4.1 joules per gram degree Celsius. Find the change in temperature. Here, we have to pay attention to what's happening. It says heat is absorbed. So this tells me that this is a positive value. Please make sure you pay attention to that. So here, I'm going to list up my values, and then we're going to figure out which each one is. So here, I know that I am going to find my change in temp. That's my X value. In the problem, it says that my Q, which is joules, is 1,674. And then for my change in temp, we already said we're finding that. My mass, we are not given that directly. My CS is 4.10. Now, we are not given mass directly, but we are given density. So we have to do something with this. And we are also given the volume. We have learned density since you guys were in chemistry. Remember, density equals mass divided by volume, which means if I know my density as being 1.10, I don't know my mass, but I know my volume as being 25 milliliters, you can actually solve for this to get your mass. So you can take 1.1 times 25 equals X. So you can find out that your mass is actually 27.5 grams. From there, we have everything that we need, so we can go ahead and plug it into the equation. 1,674 equals x times 4.10 times our 27.5. Here with our algebra skills, we're going to combine terms. So this one is going to equal 112.75x divided by the number attached to x. We're going to find out that x equals 14.847000665. Here is where a lot of people are going to see an issue. This is going to tell us our change in temperature, and that's what we're looking for. But when you do problems like this, make sure that you're paying attention that it's not asking for final temperature. If it's asking for final temperature and it gives you an initial, you can subtract them. If it's asking for initial temperature and you're given the final, you can subtract them. So pay attention and make sure you're solving for what you're asking for. Here, if we're rounding to the correct number of sig figs, 14.8 degrees Celsius is my change in temperature. And this positive 14 means I've increased by 14 degrees. With that being said, let's actually find and do an example where we're finding the final temperature. So here it says 1,000 grams of a metal at 53 degrees Celsius releases 6,688 joules. If the metal's specific heat is 0.352 joules per gram Celsius, what is the metal's final temperature? So Q, mass, CS, and delta T. Here, my Q is going to be my heat. Pay attention to the wording. Releases. That means that this is a negative 6,688 joules. Your mass is 1,000 grams. It's in the correct units, so we're okay. Your specific heat, it tells me, is 0.352. And then over here, it gives me a temperature, but don't get confused. It says that it's at this temperature. It didn't say anything from increasing from this to this. It didn't say anything about increasing 53 degrees. It didn't say anything about decreasing 53 degrees. So this is not giving a change in temperature. This is just stating a temperature. In fact, this is actually stating the initial temp. So again, words matter. Here we can plug in what we know. Negative 6,688 equals 1,000 times 0.352, and I don't know my change in T, so I'm going to put X. Let's do our algebra to combine them. And then when we actually solve for X, we get a negative 19.0 as a change. What this means is that my temperature went down negative 19 degrees. So I can actually take my initial temperature, which is 53. This means it went down 19. So when I actually calculate this, this is 34.0 degrees Celsius for my final temp. Okay. That's the end of today's lesson, and if you have any questions, please make sure that you ask, and I hope you guys have a great day.